Hello everyone, my name is Isaac, and in this notebook, we will be exploring some machine learning techniques for classification. In the first code cell, we are importing the necessary libraries for our analysis. We will be using NumPy and Pandas for data manipulation, SciPy for statistical analysis, Sclearn for machine learning, Tabulate for creating tables, and Matplotlib for data visualization. We have also set the plot style to ggplots. Let's move on to the next cell. In the previous Markdown cell, we learned about Gaussian distribution and its probability density function. In this code cell, we will visualize the Gaussian distribution using NumPy and Matplot libraries. In this code cell, we defined a function called Gaussian that takes in three arguments, gz, min, and isteva. The zg the isas argument can be a float, int, list, or NumPy array. The mean argument is the mean of the distribution, and the isteva argument is the standard deviation of the distribution, which is the square root of the variance. The function first checks if the type of AIs is not a NumPy array, and if it isn't, it converts it to a NumPy array. Then the function calculates the formula for the Gaussian distribution using NumPy functions. The formula is $fx f fractione sigma ne c rt tuapia a fractione tu fractamut u fractamut sigma tu $. Where $$ is the mean and $, is the standard deviation. Finally, the function returns the probability density value for the given xi input value. This function can be used to calculate the probability density values for any Gaussian distribution, not just the standard normal distribution. Let's move on to the next cell. In this code cell, we are generating 1,000 evenly distributed values in the range of AMU5, 5, 5, 5, 5 using the NP linspace function. These values will be used as inputs to the talk Gaussian function we defined earlier. Then, we are plotting the results of the Gaussian function over the range of AG5, 5, 5, 5, 5 using the tplot a function. We pass in the xi values as the first argument and the Gaussian, the function with mean 0 and standard deviation 1 as the second argument. We also set the title of the plot to a Gaussian distribution over OT5, 5, C using the epltitle function. Finally, we display the plot using the plot show function. This code cell generates a plot of the standard normal distribution over the range of 5, 5, 5, 5. The plot shows that the probability density values are highest at the mean, 0, and decrease as we move away from the mean in either direction. In the following text, the author is suggesting that instead of writing our own function to calculate the Gaussian distribution, we can use the itescpy stats library, which already has a built-in function for it. In this code cell, we are again generating 1,000 evenly distributed values in the range of AND 5, 5, 5, 5C using the ENP linspace function. Instead of using our own Gaussian function, we are using the tpdf function from the stats normous object in the scpy stats library to calculate the probability density values for the standard normal distribution with mean 0 and standard deviation 1. We then plot the results using EIPplot, passing in the UX values as the first argument and the UATPD VEF function as the second argument. We also add vertical lines at the mean and at one standard deviation away from the mean using ipldxvline. We annotate these lines using iplet annotate to indicate what they represent. Finally, we set the title of the plot to a standard normal distribution using epltitle and display the plot using epl show. This code cell generates a plot of the standard normal distribution with mean 0 and standard deviation 1. the plot shows that the probability density values are highest at the mean 0, and decrease as we move away from the mean in either direction. The vertical lines and annotations help to visualize the concept of standard deviation and how it relates to the distribution. In this code cell, we are defining a function named Multivariate EPDF that takes in a numpy array mean and a numpy array mean and a numpy array covariance. The function first calculates the determinant of the covariance matrix using np-lineal gdet. If the determinant is 0, the function returns 0. If the determinant is not 0, the function calculates the inverse of the covariance matrix using np-lineal gnt. Lineal j np a yen, ben txo nt, exp, e, csc. The function then calculates the final probability density value using the formula for the multivariate normal distribution that we saw in the previous text block. Finally, the function returns the probability density value. This function will be used later to calculate the probability density values for a multivariate normal distribution. In this code cell, we are generating a dataset with 100 random features from a normal distribution with mean 10 and standard deviation 5, and 100 random features from a normal distribution with mean 18 and standard deviation 2. We then calculate the actual means and standard deviations from our feature sets using npm-mean and ntste. Next, we create a multivariate distribution using stats multivariate normal, given our means and standard deviations. We then add 5 anomalies to the dataset, which are points that would not be in the normal distribution. These anomalies are added to Oxonea X2 using np-appapam. Finally, we calculate the probability density values for our features using edist-pdf and store them in the variable proboa. This dataset with anomalies will be used later to demonstrate anomaly detection techniques. In this code cell, we are creating a scatter plot of our dataset with the probability density values as the color of each point. We first set the figure size using iptot figure size 10, 6. We then create the scatter plot using eplot scatter with oxone and ox2 as the x and y coordinates and eproba as the color of each point. We set the title of the plot using plot title and label the x and y axes using iplot x label, and dplot, label. We then annotate the 5 anomalies in the plot using usplot annotate. Finally, we add a color bar to the plot using epl.colorbar, adjust the layout using eplot title layout, and display the plot using eplot. Show. Duh. The resulting plot shows the distribution of our dataset with the anomalies highlighted in red. In this code cell, we are creating 2 scatter plots side by side to visualize the identified anomalies in our dataset. We first create a figure with 2 subplots using efig, axone, ax2, ptt, subplots, nrows1, ncls, 2, fig size, 10, 6. We then set the value of u in A7 and create the first scatter plot using axone scatter, with oxonea and ox2 as the x and y coordinates, and EAP, where, probodeps, red, p, blue, as the color of each point. This sets the color of points with probability density less than epc to red, indicating that they are anomalies. We set the title of the plot using axone. Title, set to text, and label the x and y axes using axes using taxone sets a label, and axone set y axes using axone set ni label. We then set the value of ypsi to eone9 and create the second scatter plot using cx2 scatter with the same settings as the first plot. This time, points with probability density less than teps are colored red. We annotate the 5 anomalies in the plot using coordinate. Finally, we adjust the layout using eplot type layout and display the plot using eplot show. The resulting plots show the identified anomalies in our dataset for 2 different values of UEPs. In the next code cell, we will import necessary libraries and load the wine dataset from the UCI machine learning repository. We will then print the shape of the dataset to see how many samples and features it contains. In this code cell, we are preparing our data for anomaly detection. First, we load the wine dataset from the UCI machine learning repository using eLoadMat function from FONSESAP IOA. We then create a data frame from the features of the dataset and name the columns accordingly. Next, we define the anomaly targets using AudioTrueWineTrueBeflatten. We select the features that follow a normal distribution using the Shapiro-Wilk test for normality and store them in the features. We also log scale some of the columns to normalize them. We then identify outliers using the mean and standard deviation of each feature and exclude them from the training set. We create a multivariate distribution given our means and standard deviations using stats multivariate normal. Finally, we calculate probability density values for our features for all values using edist-pdfc. This prepares our data for the anomaly detection process. In this code cell, we are creating a box plot of the scaled features in our dataset using the funimanimaxscala function from the ANSYS-Clearn preprocessing module. First, we create a new figure with a size of 10 by 6 using the tplotfigure function from the tmatplotlib pyplot module. Then, we create the box plot using the typlotBoxPlot function and passing in the scaled data from our data frame FET using the onDemandMaxScale function and selecting the columns we want to include in the box plot. We then set the xsticks using the eplotxsticks function to label each box with the corresponding column name. We also rotate the labels by 90 degrees to make them easier to read. Finally, we set the title of the plot using the ptoid-title function and display the plot using the hyplotShow function. This plot will help us visualize the distribution of our scaled features and identify any outliers. In this code cell, we are evaluating our model's performance with different epsilon values. First, we create an array of 21 equally spaced values between 0.001 and 0.01 using the np-linspace function from the numpy module and assign it to the variable eps. Then, we create empty lists for IRCall, tPrecision, and nNOS. Next, we loop through each value in tepsa and perform the following steps. We use the usnp, where function to classify each observation as either 1 or 0 based on whether its predicted probability is less than the current epsilon value AWAC. We calculate the recall, precision, and aux scores for the predicted labels using the TARACall score, precision score, and IROCOTIO score functions from the TANSCLEARN metrics module, respectively. We append each of these scores to their corresponding lists. By evaluating our model's performance with different epsilon values, we can determine the optimal threshold for classifying observations as anomalies. In this code cell, we are visualizing the evaluation metrics for different epsilon values using a line plot. First, we create a figure with a size of 10 by 6 using the tplotfigure function from the tmatplotlib pyplot module. Then, we plot the recall, precision, and aux scores against the epsilon values using the eplotplot function. We also add a label for each line using the onToLabel parameter. Next, we add a vertical line at the optimal epsilon value of 0.0065 using the tplot oxyfline function. The line is colored green with an alpha value of 0.3 and a line width of 40. We add a title to the plot using the plotTitle function and a legend using the plotLegend function. Finally, we adjust the layout of the plot using the FileTitle function and display the plot using the setPlotShow function. In the next code cell, the epsilon value is set to 0.0065 and the confusion matrix is calculated. In this code cell, we first use NumPy's where function to classify each data point as either a positive or an anomaly based on whether its probability score is below the chosen epsilon value of 0.0065. Then we calculate the confusion matrix using the cConfusion matrix function from the tscleren metrics module. We pass in the true labels, the true labels, the true, and the predicted labels. Pret. We then create a pandas data frame from the confusion matrix with the predicted positive and predicted anomaly as columns and the true positive and true anomaly as rows. Finally, we print the data frame using the tabulata function from the tabulata module with the tFNC grid table format. In the next code cell, we will plot the data points and mark the anomalies with red circles. This will help us visualize how well our anomaly detection algorithm is working. We start by creating a scatter plot of the data points using matplotlibscatter function. We pass in the feature values x, 0 and x, 1 as the x and y coordinates, respectively. We also set the marker size to 7 and the color to blue. Next, we use NumPy's where function to find the indices of the data points that are classified as anomalies. We then use these indices to create a new scatter plot with the same feature values, but with a marker size of 70 and a color of red. Finally, we add a legend to the plot to indicate which markers represent anomalies and which represent normal data points. We also set the title of the plot to show anomaly detection. Great job explaining the code, Isaac. To summarize, in this Jupyter notebook, we implemented an anomaly detection algorithm using the Gaussian distribution and applied it to a dataset of server latency and throughput values. We used the trained model to classify each data point as either a normal point or an anomaly based on a chosen epsilon value. We then evaluated the performance of the algorithm using a confusion matrix and visualized the results with a scatter plot. Overall, this notebook provides a good introduction to anomaly detection and demonstrates how to implement a simple algorithm using Python and popular data science libraries such as NumPy, Matplotlib, and scikit-learn. Thank you for watching this tutorial, and I hope you found it helpful.